Good morning. It's a pleasure for me to introduce to you Professor Jeff Kuhn of the Institute for Astrophysics in Hawaii. I've known Jeff since 1979 when he was a graduate student, and he was one of the fastest theses in the history of Princeton physics. 2.5 years he was out the door.
You made that up.
No? February 81, you were out the door. In any case, he's mostly done his work on the sun, and he was the first one to determine that the temperature of the sun was slightly hotter at the equator, I think, than at the pole, at the time by 6 Kelvin, which was a 1 part in 1,000 measurement. The sigma was 1 Kelvin. He's continued to do breakthrough work on the sun. He's going to tell us on Monday at the solar seminar about a recent paper of his where the photons that the sun emits exert a torque and actually affect the rotation on the surface, which is as many of Jeff's results being breakthroughs, a controversial result. Jeff has also built instruments. He built the first infrared CCD on a telescope. He put together one of the first robotic telescopes because the Solar Oblateness Telescope on Mount Wilson ran for a long time unattended. Of course, it was an easy thing. The sun was always, it was their only target, right? Although the right ascension and declination changed. But that telescope ran unattended in, what was it, 1986 or 88 or something like that, right? He's also contributed to non-standard theories on dark matter, and he's worked on clusters of galaxies and is in the Guinness Book of World Records for having observed the largest galaxy in the universe. So he's not just a solar astronomer. He has designed telescopes. He's been the PI for a number of them, off-axis telescopes. His design with Gil Moreto, I think, is what's the large giant Magellan telescope. And he's also contributed many of the ideas behind DKIST, which he will also discuss on Monday in his talk, which will be at 10:30, I think, also here. With that, we're discussing whether we can collaborate on making new telescopes with a new design and doing some exciting science with it. And Jeff, tell us all about it.
Okay. Thanks, Juan. So I was actually here many years ago. I don't remember very much, but I do remember your kind hospitality, and that hasn't changed. Thank you for the invitation, and I'm enjoying my time here, and I'll be here for a week. I'd love to speak to many of you. So this is kind of a weird talk. There's a little bit of science. It's a little bit of physics. Mechanics and F equals ma kind of physics, and then some technology. And what I want to try to do is lead you through a different way of thinking about optical telescopes. So this problem started for me about 4 or 5 years ago when a person of means, Rafa, that's Casey Harlington if you haven't seen him. Casey, when I was the director of the Maui Observatory, came. He's a crazy man. But he came and he said, like, I got some money. I'm really interested in astronomy. He was taking some courses from a distance to learn astronomy. And he said, I would like you to get a group of people together and think about what we could do if we had a blank page. If we had a blank page and we were faced with trying to build a telescope that's really good for exoplanets and possibly this problem of detecting ExoLife. And so there have been 3 or 4 meetings in those, actually 4 meetings in that time. It's a partnership now that includes some engineers, the engineers that designed the Canada-France-Hawaii telescope, and they're responsible for the TMT enclosure design, and then some optical scientists, and then just a few astronomers, not very many, along with some folks that do interferometry. So the Chara folks are engaged in this group in the Georgia State University. And that's part of the theme of this talk is if we think about the next generation of telescopes beyond Grunticon and beyond TMT and EELT, what would they look like and what would we have to do to get bigger than what we have? So here's the roadmap. I'll talk a little bit about what we could do. I want to hammer on this point that the size of the telescope is a really important thing for the problems that we care about if we're looking at exoplanets. And that's really about wavefront control, and I'll show you the optical concept, and we'll talk about what I think is the perfect coronagraph. And then I'm going to lead you through some of the technologies that we're doing with our French colleagues at INSA in Lyon. This is a group that has specialized in the development of piezos. And the new technology, which I think is really exciting, are called electroactive polymers. And we've spent the last 2 years learning quite a bit about what we could do with those. So the science problem is this direct imaging of exoplanets. And imagine that you're looking at an exoplanet. It's orbiting a star a long way away, and the exoplanet is rotating. Are we good? I feel better. Okay. The exoplanet is orbiting and rotating, and if we could measure the light curve, the integrated light of the exoplanet, you might see a curve that looks like this, where each one of these bumps is a day, an exoplanet day, and the whole curve is the seasonal variation of the light flux. We can't build a telescope that's going to resolve structure on the exoplanet, but I believe we can build a telescope, essentially now, as you may know, that is able to resolve and separate the light of the exoplanet from the light of the star. So it's an interesting problem that if you took the Earth and you put it at the distance, say, of Proxima b, and you integrated the light signal from that rotating planet, and here's a simulation where we took the Earth. We know the albedo of the Earth from NASA satellite measurements very well. This is a map that's been applied to this simulated exoplanet. And here's a year of simulated exoplanet time, and each one of these is a day. And here's 3,000 photometry observations. And we solve the inverse problem where we have 1,800 pixels distributed in latitude and longitude on the exoplanet. And now you probably know that there are folks that invert for pictures of stars, the sunspot distribution or the magnetic field distribution, by using the rotational information. It's a slightly different problem because we have reflected light from the exoplanet, which is varying due to the rotation and the albedo variation of the surface of the planet due to the rotational motion and due to the orbital motion, and that's what has been simulated here. The signal to noise in the observations is good. It's 200. And if you now do a least squares inversion and ask, what does the surface of the planet look like, even when we have a telescope that doesn't come close to resolving that, the answer is it's pretty darn good. We can make maps of exoplanets. If we can do photometry at the level of a few percent, and if we can dedicate instruments to be able to get the time needed to follow the orbital and the rotational periods of those planets. We need a little bit of signal to noise. How good does the signal to noise have to be? Well, here's another simulation where the signal to noise is only 20. We only had 400 data points, and again, the surface of the planet has a resolution of 1,800 pixels in latitude and longitude. And again, the inversion problem looks like this. Well, it's not nearly as good, but we can see their continents, and we can see that there's an ocean. And we can see that as an albedo map. So, and imagine that you do this not just as a function of a broadband color, but you do it as a function of multiple colors. Or you do it as a function of broadband infrared wavelengths. We could measure temperature, or we could look for the green edge of the Amazon, the equivalent of an exo-Amazon, or the reflective color variation of a desert. Plenty of photons in a big telescope if we can do this problem of time-resolved photometry over long stretches of time. My guess is even if the EELT could do this problem, you wouldn't get time to do it. It was a little bit of a surprise that even if we took, say, a real Proxima b, which is tidally locked, probably, if it's tidally locked, because the part of the surface of the planet which you see, which is illuminated, is varying because of the orbital motion, we can still get information about the existence of continents and oceans on this sort of a scale. So this is pretty exciting to us. We thought if it were possible to argue and demonstrate that we could be looking at the surfaces of exoplanets for life or evidence of technology, this is the telescope. A telescope that can do this is worth some effort and energy. Now this just shows that if you scale back what you want, just from the light curve, we can measure inclination parameters without knowing what the surface looks like. So there are lots of things we'll learn and we'll determine about the exoplanets and their geometry, even without pushing forward to get maps of the surface. It was interesting to me to compute the thermal effect of the power that human civilization consumes. So all the power that we use gets turned into heat. And the total amount of heat that we produce, divided by the total heat energy of the Earth, is a surprisingly large number. It's this number right here. So this is, if we consumed all of, and therefore radiated, the equivalent of all of the energy that the Earth receives from the sun, that this ratio is 1. The present global power production all turns into heat, right? I mean, our cell phones, we use the energy, and the work that's done is heat. That heat is a half of a tenth of a percent of the total energy that the Earth radiates due to the solar energy that we intercept. That's a really big number. That is also an unavoidable global warming problem. For comparison, we know that the sun varies in its brightness by 0.1%. We're already at a half of that in the amount of heat that we produce, not because of ozone issues, but because of the power that we use. And in fact, if you look at this power scale from a long time ago to present, that number is only increasing. So when we dredge up coal or we use uranium or we use oil, we're producing heat, and that heat is a global warming problem. Of course, the solution, right, is to take the energy from the sun with photovoltaics, use that energy to do work, and then return that heat back to the environment, and we don't have this global warming problem. And presumably, in an exoplanet, if it was an exoplanet that had civilization, they would have figured out how to do that. And so there's an interesting signature to think about, which is if we were to look at an exoplanet which has got civilization on it, this albedo effect where we absorb sunlight and we do work with the energy and then we return the heat to the environment, means that a planet, if we could find it, which was dark optically but infrared bright, is maybe a good candidate for actually advanced civilizations. Anyway, so the heat signature of life is a really interesting heat signature, and it's not just civilization. The photosynthetic global power consumption of all the plants is actually larger than the present global power production of coal and oil and gas and the things that we usually think of. The optical power, in comparison, is more than an order of magnitude less. So if you want to use electromagnetic signals of life, you're much better going to the infrared than trying to look for example, city lights. City lights are much fainter in terms of their energetics. Well, it's also interesting to think about when we look down on the surface of the Earth. This is a plot that shows the temperature excess which is measured, and of course, I grew up in Michigan. Here's Detroit, here's Chicago. Those temperature excesses, right, are very significant. They're several degrees out of 300 Kelvin, which means delta T over T, if we could resolve any of that temperature structure, is a signal which is of order 10 to the minus 2. The global thermal signal of a civilization, if we could measure this number, is a few times 10 to the minus 4. But the thermal signal is a biomarker which is pretty interesting. Of course, you can think about ways of defeating it. Well, a planet that has volcanic activity has a big thermal signal. But of course, a trademark of heat which is returned into the environment efficiently will be temperatures that are close to the ambient temperature. So part of the argument for looking for life will involve looking in multiple bands and measuring the temperature structure and using the rotational signature. This was just an exercise that we did, which was to say, well, let's suppose that this is an advanced civilization, and the civilization has reduced the albedo here because this energy is being used by the occupants of the planet and then being returned to the planet as heat. Could we see that through this sort of rotational observation with a signal to noise of 200? And the answer is yes. So this was just an exercise to show that if we could start to do this sort of photometry on an exoplanet, there are a lot of interesting things that we could do related to finding life. So there's several lessons in this. So that's a picture of Keck or Grand Teton. Give it a diameter d. If you build a diffraction limited telescope and you ask the question, how long does it take to achieve, so it's a diffraction limited telescope, you're looking for a faint signal in the presence of background noise, a point source, in the presence of background noise. As you make a telescope bigger, the diffraction limit gets smaller, just the airy disk. And the time to achieve a certain signal to noise scales like 1 over the diameter of the telescope to the 4th power. Size matters. There's another interesting number, which is that if you're controlling the wavefront, so you build a telescope and you have an optical surface, and the optical surface is doing something to the wavefront, like think of an adaptive optic system, and you have a phase error. Every optical system has a phase error. If that phase error is distributed, so the same amplitude of phase error is distributed over a larger diameter optical system, the phase error converts into an electric field that's distributed not just at the core of the image, but a diffuse halo. That diffuse halo, the amplitude of that intensity, scales like 1 over the diameter of the telescope squared. So not only do you have this enormous advantage in detecting a faint signal from a bigger optical system, but you have an enormous advantage when you build a coronagraph or an instrument that depends on controlling the phase of the wavefront at the pupil by making the pupil bigger. If we're interested in, say, taking a census of exoplanets for life, that's a problem which is an angular resolution limited problem. Right? And the angular resolution sensitivity of the telescope is going to scale like the diameter of the telescope. And the volume that we can sample for a given diameter telescope must scale like the diameter cubed. The diameter gives the distance to which you can measure at the given angular resolution. And so there's also this huge advantage to, if we're interested in studying and understanding exoplanet systems, in having a larger volume to be able to look into. So everything gets better with the size of the telescope. And so when we talk about, well, it's really NASA where we're going to, or space experiments where we're going to do exoplanet studies, that's true for transiting observations where it's not direct imaging. But once we get to the point where we want to understand the light and the structure of the exoplanets, it's going to be done from the ground with telescopes that are as big as we can possibly make them, because there's this enormous advantage in almost every metric that we think about. So this is the landscape. You may remember OWL, 100-meter telescope. It's in some of my graphs because it was studied very carefully. We know, I think, how much OWL would cost. We know pretty well how much TMT will cost in GMT and EELT. Those costs are all known, and here's some examples about space experiments. In this landscape, will these telescopes do this problem that that we're describing here? My answer is probably not, for several reasons. One is that these telescopes are designed for a large community, they're wide field, and their optical performance is set to be able to look at a fairly big piece of the sky and to look at quasars, galaxies at a redshift of a lot. The telescope that we're talking about and we're proposing is over here on the same footprint scale. It's about 25 meters, and it's not a filled aperture, but we want to think about it as this sort of hybrid optical telescope, which is a combination of interferometry and optical systems. And you'll notice that it does not multi-segment the pupil plane by a lot. And in a minute, I'll show you why that's really important if we're interested in looking at faint things next to bright things. So the first problem is we've said that D has to be really big, but D costs a lot of money. And if we look at all of the telescopes that I know about, the typical scaling factor for Keck-era telescope designs, so Grant-de-Kahn and Keck, TMT and EELT, they're all essentially the same mirror substrate design, is 2,000 kilograms per square meter, and the cost, turns out, of all of these telescopes scales with the mass. For the moving mass of the, we call it the payload, the optical payload in the system. And the typical cost is sort of a third to $1 million per metric ton. And that number works for all of these telescopes along this line. There's one telescope, which is 100 meters across, which completely breaks the scaling relationship. Its cost is $0.013 million per ton. And you know what that telescope is, right? That's the off-axis Green Bank telescope. And it's 100 meters across. The surface RMS, instead of being a fraction of an optical wavelength, is a third of a millimeter. And the reason why it's a lot cheaper is because it's not nearly as stiff. So its mass is a lot less, and so its cost can be proportionally less. So it's a question of the stiffness of the optical system. So optical telescopes are expensive because they're massive as they get bigger, and because the stiffness that we need to create a wavefront, which allows us to do the sort of wavefront control to be able to see faint objects next to bright objects, is hard. So this is the problem, right? It's the problem of looking through the glare of the headlights to see the color of the driver's eyes when they're just emitting in the thermal wavelengths of whatever the body temperature of the driver is. The glare problem. So you probably know that if we take a planet in the habitable zone and we look at the reflected brightness or the emitted brightness of that planet as a function of the temperature of the star, as the temperature of the star goes up, the contrast, the integrated brightness of the planet, is a tiny, tiny fraction of the brightness of the star. And that, of course, the reason is that the habitable zone moves in closer to the star as the star temperature drops. That's why we're all excited about these cool stars that have habitable zones that are nearby. The Earth around the sun, as you know, is a 10 to the minus 10 contrast problem. We're not going to do that very soon, and it's probably not all that interesting. But if we go to the infrared, the problem gets rapidly better, and it can even be a 10 to the minus 6 or a 10 to the minus 4 problem in contrast. Those are numbers that we can handle. We do that in solar physics all the time, right, Manolo? 10 to the minus 4, 10 to the minus 5. If you have enough photons, you can do amazing things, and that's why we want a big telescope. You don't want it to look at faint galaxies. You want it to have enough photons to be able to do important problems like this. So telescope scattered light, even in an ideal telescope, has a lot of sources. So this is essentially the surface brightness as a function of the log of the distance. This is in a telescope that doesn't have adaptive optics. And so when you put a spider and a secondary in a conventional telescope, the The surface brightness is this curve over here. And once you get a couple of arc seconds out, this is visible, this is infrared, that spider brightness, if you've looked at images of bright stars in telescopes, once you get a couple of arc seconds from the core, it dominates what you see. The atmosphere, this is an R naught equals 10, is there's no AO here. Of course, that will change when we put AO in a system, is above all of this, and that dominates the core of the image that we'd be looking at. The mirror roughness is this dashed line right here, and it eventually dominates the scattered light at short wavelengths. If you go to the infrared, for the mirror roughnesses that we can achieve, it doesn't matter anymore. The aperture diffraction is this dotted curve. The aperture diffraction, as you go to the infrared, eventually dominates, but we'll build coronagraphs and we'll control the diffraction pattern. And I'm going to show you how we do that before we let the objective and the other optics in the telescope scramble the light. So that's an ideal telescope. This is Keck. So this is a Keck image taken with a reasonable AO system. This is the derived wavefront on Keck, and it's pretty ugly. I don't know what Grand Teton looks like, but we can see every one of the segment boundaries. And the segments are only a millimeter. Right? The problem is anytime you polish a mirror, the polishing tool at the edge can't help but create edge errors, although there's now hope that TMT and other telescopes will make those edge errors much smaller, but you're seeing those edge errors. Keck has a problem with the support at the center of each one of the mirrors. It's a well-known problem, but the combination of all of these phase errors creates a PSF after you take away the atmosphere that looks like this. There's 3 orders of magnitude in that intensity display, and there's 0.2 arc seconds across. Try and find an exoplanet with that PSF. This is just the residual. So when we multi-segment a telescope, we've created a bunch of phase errors that we now have to pay for when we want to look for the diffuse signal of something which is in the nearby presence of a bright star, the exoplanet signal. It's really hard to do the kind of problems we're talking about with a multi-segmented telescope. And I'll be quantitative with that in a minute, right here. So if we were to build a telescope and ask ourselves, could we see Proxima b with a coronagraph that has the scattered light performance of SPHERE? So SPHERE is this European system. Who was the lead on it? Observatoire de Lyon was part of it, and many others. It's on the VLT, the 8 meters. And we ask ourselves, as a function of the aperture, what kind of signal to noise could we achieve looking at an Earth at the distance of Proxima b? Here's the albedo that we assumed when we took 1 hour of integration, and this is the signal to noise. And I showed you earlier that if we could get a signal to noise of 30, 200 would be even better, then we're in business to do a bunch of really interesting things. And guess what? We can't do it with the telescopes that we have now. Once we get to about 20 meters, good things happen. That's where we want to be. That's a sweet spot for getting started with this problem. Another way of looking at it is, given the exoplanet systems that we know about and the telescope diameter, how many of them could we do this interesting imaging of the surfaces as a function of the aperture size? And it turns out once we get over here to 20 to 30, we could do tens of systems. I claim that's an interesting number. This is where we get a full image of the system. There are many other systems that we would use such a telescope for to do other less ambitious programs. If we take a highly segmented telescope with mirror sizes that are of order 1 or 1.4 meters across, here's one with 50 segments. The number drops by more than an order of magnitude. Here's 500, here's 800. Because now we have to cope with the diffuse background of what you saw in that Keck image. And I know that EELT claims that they'll have much smaller wavefront errors than Keck, and probably they will. But they're starting from something like this to try to do these high contrast problems. Okay, so you got your blank piece of paper. You know what the physics are that we have to struggle with. We're building a telescope for the exoplanet community. What should it look like? Well, it has to be big. It's all about diameter. But we have to be able to afford it, which means it has to be light in mass. We don't care about the field of view, right? We're always going to have a bright star, the host star of the exoplanet, and we don't need a field of view that's any more than a few arc seconds. That means that it can be a very fast focal ratio, and the volume of the telescope can be small. That means it's less expensive. That scales the cost. There's always a bright star on the field of view. We're going to use stellar photons to build essentially an interferometer, an active optical system, as good as we can do it. Not just conventional AO, but AO that goes beyond what you're used to thinking about. We're not going to use mass. So mass in telescopes is used to make them rigid so that they don't deform as the optical payload tracks. We're on the Earth, we're not in space. We have to track, and as we track, the mirror will distort, and we have to be able to control that. We're not going to use mass to create stiffness. It turns out we can do that, we know, with the physics of these materials that we're using with ENSA. Make the optical mechanical structure. So the other thing that we want to do is, so we build these telescopes. We make the optical surfaces match to a fraction of a wavelength, and we look through the atmosphere, which introduces many waves of optical distortion. Why are we wasting our money and energy to make an optical surface that's rigid and then build an AO system that has to correct it? The optical surface doesn't need to be any more rigid than the wavefront aberrations that are produced by the atmosphere that we're looking for, that we're going to correct when we make our diffraction limited system. So we don't have to make the mechanical structure very stiff. That also means it's less mass. It means it's not as expensive. Okay, that ends up, I'll explain what the optical configuration here is, what a Fizeau interferometer concept is. We're going to correct the wavefront errors at the telescope, not after phases have been scrambled by telescope diffraction. This idea is create an optical system that has a synthetic diffraction profile that does what you want it to do to look for and measure faint objects next to bright objects. Let me explain what that means as we go through this. So the technology elements are, this is a telescope concept. It has an odd number of optical systems, and that has to do with the fact that the baselines, the differences between the centers of each of these mirrors are non-redundant. You put a bunch of optical systems on a circle, and you put an odd number there, and there's the multiplicity of the difference vectors between the centers of the objects are non-redundant. It has a great optical advantage. Furthermore, each one of these is an independent telescope. That subaperture has its own elliptical secondary mirror that produces a focus down here, which is essentially a Gregorian focus. Each one of these mirrors is cut from the same parent parabola. So each one of these mirrors is identical. It's just a surface of revolution from the parent parabola, as are each one of the elliptical mirrors that correspond to each one of these. So the light comes from the universe, bounces off of a mirror, bounces off a secondary, and forms a focus down here. This, you can see, is a very fast optical system. It doesn't have much volume in this direction. That's a good thing. So imagine that each one of these is an adaptive optic system. So imagine that we put an adaptive secondary for each one of these, and we figure out how to measure the phases, and that adaptive secondary creates the atmosphere on this part of the subaperture. Then we will have a bunch of diffraction limited images. What happens if we combine each one of those diffraction limited images on top of one another back at this image plane right here? Do we get a coherent image? The answer is no. because the AO system doesn't correct the tip tilt very well, and we don't have control over the piston phase with an AO system. So there's a piston phase error between each of the subapertures, and when we combine them all, what we'll get is a bunch of speckles, and the energy is not in a core image right here, but it's distributed around each one of the speckles. And each of the speckles has the diffraction width of the full optical system, but the spread of those speckles over the field of view is defined by the diffractive width of the subapertures. I'll show you what that means in a minute. But what we have to do is we now have to make this work as a coherent optical system. We have to find the piston and the phase errors of each of those optical elements. But you could guess that it's somehow encoded in that speckle pattern, right? And that's the problem that we have to solve. The next point is that we're going to create a coronagraph at the telescope pupil before the light goes any further. And we're going to minimize the subaperture mirror mass and cost with a bunch of this really, really cool technology. And the technology is what we're doing over in Lyon. Here's a picture of one of our mirror actuators, and I'll show you how that works. Okay, so is there a scalable optical configuration that combines interferometry with fixed pupil concepts? Of course there is. This is what it looks like. Okay, so each one of these comes from the same parent parabola. That's an elliptical mirror, and it basically takes the focus of each one of them and transfers it down to a common focus down here. This is a bicycle wheel. Bicycle wheel is one of the most efficient structures that gives you stiffness when you ride your bike, but it doesn't collapse and it doesn't have very much mass. And that's because this combination of mechanical elements that are in tension and compression. The combination of tension and compression is a mechanical subject that's called, Buckminster Fuller coined the term tensegrity. We can minimize the mass of the optical system by using a bicycle wheel to create the structure and to put the mirror segments around that, to put each of the secondaries over here, and the instrument focus comes down here. The secondaries, by the way, are these little tiny things. The field of view is small. Each one of these is an off-axis parabola, my favorite optical design, and it creates a common image. It's not like when we tend to think of interferometers, we think of a flat, and the flats steer the light and combine it. There's only one baseline in that case. This is the full image, the full UV coverage of each one of these is being combined to create the interference of each of those images, which creates that speckle pattern. Okay, so the question you want to ask is, do we have a hope of teasing out all of that information to be able to affect the relative phases of each one of these subapertures to make a coherent image, which is what we want to get? And the answer is yeah. So I'm late to this game of machine learning, but I'm learning. And a graduate student just over the last few months has shown us how this is a perfect machine learning program. Because what these images show is the diffraction pattern, the full diffraction pattern of 15 subapertures when they're phased properly. And this is a logarithmic scale, so there's, if you looked at this on a linear scale, you'd just see that peak at the center right there. Okay, so what is the structure here? So the small scale structure is the interference pattern generated by the large scale pattern of mirrors. The larger angular rings are the diffraction structure of the subapertures, and they're much smaller, and so their angular scale is much larger. If we take that perfectly phased set of mirrors and we now add piston errors to all the mirrors, this is what that would look like. The image is changed. You see this sort of worm-like pattern of intensity, which are now the speckles, created by the piston phase errors of each of the subapertures. The diffraction rings of each of the subapertures are largely unaffected. If we now take not just piston errors in the optics, but we allow for tip-tilt errors in the optics, the diffraction pattern looks like this. So my reason for showing you this is that in the image, somehow, are encoded both piston phase errors in the mirror and tip-tilt errors in all of the mirrors. And we can work out some analytic expressions that show how you might compute those, but it works a whole lot faster to put this into a neural network, a convolutional neural network. And here's, you guys probably know more about this. I'm just learning about this now. So it's a convolutional deep neural network. It's essentially the construction of a function that takes an image and spits out the tip-tilt and the piston errors of all the mirrors just by looking at the intensity image of the speckles. And it's magic. It's not really magic. It's a reconstruction of an arbitrary function done by simulating 1 million of these images, where we randomly put in piston errors or we randomly put in tip-tilt errors. We know what the proper output should be because we simulated it. We do it 1 million times, and we run what is now almost standard software called TensorFlow and Keras. We have 4 layers of neural nets, and we train, which means we reconstruct the arbitrary function that knows how to take the input speckle image and output the phases and tip-tilts. Once we have that image, we can put it on your PC, and you can run it at much faster than optical rates to take an image and, by the way, know what the mirror piston phase and tip-tilt should be. That's a great thing. And so here's some results. So we have a couple of issues that aren't obviously solved by looking at those images. One is that the total range of piston error could be many wavelengths. How do we know how to solve the phase wrap problem? Is it 1 wavelength or 2 wavelengths or 10 wavelengths in piston error that would produce the same phase error at a given wavelength? Well, if we give some bandwidth to our speckle images, so the physical experiment is to take an image of the speckle pattern in 2 passbands, one say at 900 nanometers and one at 500 nanometers, give some bandwidth. Magically encoded in those images is enough information to solve the phase wrap problem. And let me show you that here. So we trained the neural network with 2-color images. So we put in a bunch of random phases for the mirrors. We created the images. We ran it through neural net software that trains and constructs this arbitrary function. And then we found out when we arbitrarily created an image and we asked, what is the returned phase? Does it work? And the answer was, for as many as almost 40 waves of piston error, the output of the neural network, what did I do? That's what you're in for. No, I don't know what I've done here. This is on my... This is a plot that shows the input on this side versus the output, and when they equal, we get a diagonal line. And for more than 15 waves plus or minus error, this neural network solution works. All right. So the point is, yes, we can build a telescope, we can make it run as fast as the atmosphere, and we can reconstruct these other elements that we need to make it a diffraction-limited optical system, even though mechanically we started with something that was floppy, and it had large errors due to the atmosphere. Let's make the telescope a coronagraph before the light is scrambled by secondary optics. Okay, so this represents the phase. When the phases of all of the mirror apertures are right, this is a diffraction pattern. It's slightly different than the other one, I think, because somehow the parameters are different. But it's not a filled aperture, so it looks not very pretty, but that doesn't so much matter. Suppose that we wanted an optical system that had a diffraction pattern which had a dark hole, no diffracted light, over here. Well, if we dial a phase into each one of these mirrors, and here's a plot from 0 to the total number of mirrors over here, and this is the phase error in radians, we can put a dark spot in the diffraction pattern. And we can move that dark spot around just by changing the phases in each one of these. And that dark spot, if we could, so this is a log plot, that dark spot is 10 to the minus 6 on average. So this was a solution constructed by some least squares technique, but this is the best coronagraph that we could make because we're using the pupil to create a diffraction pattern, which is our coronagraph, to look for something that was faint and possibly located right here. So how would we use this? So the star would be here. The diffraction pattern of the star would be the light that we see. We would dial in the phases, and we would see a dark spot right here, and we'd look for a faint exoplanet by using all of our tricks available to us to find that light. And if we didn't find something, then we would search the field by moving that dark spot around. There's another advantage of making the coronagraph with the pupil, and that is that the phase errors in a telescope map into intensity errors. And so we can't adjust the phases perfectly. So I've shown you here phase errors that are essentially 0 across each of the subapertures, but there will be some errors. And those errors are modulated by the diffraction pattern. It's a phenomenon that's called speckled pinning for the experts. The phase errors map into intensity errors modulated by the diffraction pattern of the optic. Since the diffraction pattern of the optic has a dark hole right here where we want to look for something that's faint, the phase errors go to 0 there. So unlike every other coronagraph, we're making a coronagraph which is optimal for looking for this faint object in the dark hole, because all of the errors that we accumulate will be modulated by that same diffraction pattern. That's a really good thing. Okay, replace optical stiffness created by mass with addressable electromagnetic stiffness. I'm talking slowly, I'm gonna go faster. Back in the 70s, we made telescopes by making the mirrors very thick. And the thickness of the mirror was such that when that payload moved on the telescope, it didn't deform by a significant fraction of a wavelength. So the 4-meter Mayall telescope is a good example of that. It was a very thick piece of glass. We made telescopes lighter by noticing that we can replace that with a truss structure of steel and a thinner piece of glass. The overall thickness is still significant because you got that truss back here, but the mass can be diminished. And so starting with Keck and Grant-Ticon and the 30-meter telescope, we've decreased the area mass density by adding truss structure and decreasing the thickness of the glass. And by the way, the stiffness, the mechanical constant of glass divided by its density is a fundamental property. It's, believe it or not, it's the same for glass as it is for steel. So we still have to have a fair amount of steel, but we've made a big improvement in the total mass of the payload by doing this mechanical concept. It's interesting to ask the question, we're fighting gravity, right? And when we take a piece of glass and we move it in gravity, the gravitational energy deformation looks sort of like, imagine it's deformed. This is just dimensional analysis. It's deformed, and this is essentially the mass times the height. The mechanical energy scales like the deformation squared, 1/2 xk squared, kx squared, right? X is the deformation. If we set those equal, so the deformation is equal to the gravitational energy that we're having to live with because of the motion of the glass on the payload, we find that the deformation looks like this fundamental quantity of density over Young's modulus times g times the size of the optic squared. For 10-meter mirrors, the size, that delta L is 1/10 of a millimeter. It's bigger than a wavelength by a lot. So mirrors that are 10 meters across, we have a really hard time not having them deform due to gravity, and you know that. Grand Teton has edge sensors, and the actual mirrors are 10 times smaller in diameter. And we use electrostatic energy to control the shape of the overall system. We use another energy source, not just the mechanical energy of the mirror. That theme we want to take to another level with electroactive polymers. Okay, so the idea is there are now polymers that can have an energy density sufficient to shape the mirror against gravity and also to shape the mirror against polishing needs. And we call that curvature polishing, and we know the mathematics. It's deterministic. This is the shape of a plate. The biharmonic, or this equation operated on z of x and y, is essentially the gravity distribution on the plate. The energy density of the polymers that we're going to use, so here's the idea. The electroactive polymer is nothing more than a capacitor. We put on the glass an electrode, we put down the polymer. The polymer has a large dielectric constant. That means for the same voltage, so if you took a capacitor plate, just had vacuum, and you applied an electric field, the capacitor plates will want to come together. If you put a dielectric in there, the force with which they want to come together gets larger. That's an idea that we can use to shape glass. That's an energy source that we can use to balance gravity and the deformations. If we connect the polymer to the surface of the glass with these electrodes on the top and the bottom, and the electrode on the bottom is connected to the glass, and we apply a voltage, the polymer squeezes this way and it expands that way. That expansion pulls on the glass, creates a surface tension, and it shapes the glass. And this is just to show that we have something called terpolymer now that can have a dielectric constant which is 50 to 100, and it can have a strain amplitude for voltages that we don't have a problem generating, so 10 to 20 volts per micrometer of thickness of the capacitor plate produces strains, fractional changes in the thickness, which are something like 1%. What does that mean for us? Well, let's make mirrors out of glass, which is a few millimeters thick. If you take a piece of window glass and you look at the surface of the window glass, this is an interferogram of a piece of glass. Here's a cut through that surface. You'll see that a piece of glass, like a window glass, is very smooth on small scales. On larger scales, it can have a deformation of a few microns. This is a power spectrum of that. This just shows it is very smooth. It varies like 1 over k squared, where k is the spatial wave number of the surface. These are long scales. It has a lot of deformation, and it drops off. That's a log scale by a lot. That's a great thing. It means if you make a mirror out of window glass, it doesn't have very much scattered light. The micro roughness is fantastic. The window glass has better micro roughness by a factor of 10 than almost any astronomical mirror that you create by abrasively grinding on it, cracking the surface, and then going to a lower grit to remove those cracks. If we could make mirrors out of glass which is never abrasively ground, we can make mirrors that are very smooth. And if they're thin enough, the deformations that we can produce with the energy in electroactive polymers is enough to polish the surface and to support the glass. Here's an example. So here's what a polymer looks like. This was 3D printed. So we do this in a computer. We measure the glass. In this case, we just applied an electrode. You can see this is a gold electrode on the surface. The one underneath it is attached to the glass. This is the interferogram of the surface once we apply a voltage. It looks like it's creating a deformation all over the glass, but what it's really doing is it's just locally changing the curvature. If you take the Laplacian of this function, this is a Laplacian, you see that you just recover the curvature, that's producing curvature. So think about now mirrors not as mirrors where we rub the surface to change the surface position, but we measure the local curvature, and then we apply electroactive polymer to do curvature polishing of the mirror optic. We don't have to grind on it. And that's what we're doing, and that's the idea for making very big mirrors that are never ground on, that are also very lightweight because they're made of thin glass. So if we do that, it means that we can build a telescope down here that's 25 meters, and my engineer friends tell me that they think we could build a 25-meter telescope if we get this mirror technology matured for $50 million. That's a lot less than what we're spending for TMT if we ever build TMT. And so this changes the scaling laws in a really significant and important way. Okay, so I'm done. The points I'm trying to make are that new ground-based telescopes can surpass space experiments for many exoplanet observations. And we should be planning for that. Post-Keck era ground telescopes will combine, I think the only way forward with bigger telescopes is to use these ideas that don't try to make something that's stiff, that basically create this hybrid fusion of what is an interferometer with what is a fixed aperture telescope. And what we'd really like to do is to first demonstrate the technologies with a small prototype and then build a 25-meter ELF that gets us into the regime where we can begin to do some of these problems that address, for example, life on exoplanets. So I'm done.
Thank you, Jeff. Have you thought about the Cherenkov 23-meter structure as a potential host for the mirrors that you plan to build? We do have all the details here, so take the opportunity to talk to the engineers involved there, because the cost of that mechanical structure for 23 meters is 10 million euros. Then you have to put the mirrors.
Yeah.
Have you thought of using the ring of mirrors that Magic or one of those telescopes?
I admit I don't know anything about them.
It's just
so
a suggestion. We can talk about this later, because maybe you can do this Fizeau interferometer with things that we already have available.
Yeah, that's a good idea.
I should say Jeff is giving a double seminar on Monday, but he'll be here also Tuesday and Wednesday. And he's staying in Aparicio's office. If anybody might find him, Tuesday and Wednesday.
Yeah.
Somebody else? Next question.
Was it clear, or was it just?
You mean this is glass that is, what would be what's this fundamental difference to the normal polished glass?
So window glass is made by drawing several techniques. One is it's also called float glass. It's floated across a molten surface, for example, of tin, and then a roller with a heater that basically superheats the surface to get something which is basically very smooth. It's glass which has never been abrasively rubbed to shape it. That's the problem. Polishing, ever since we started polishing glass, has been this process of fracturing the surface to change the height of locally what's there, and then coming in with a smaller size grit to remove the fractures that you created, and doing that successively. It's not often a deterministic process, and there are other techniques now. I mean, electron beam figuring of glass is another technique which is deterministic, and it removes glass in a different way. What we're suggesting is that we shouldn't, once we have a smooth surface, we shouldn't be using abrasive techniques to shape it. If we think about the curvature of the local surface and we address the curvature, which we can do from the backside of a thin piece of glass, we can undo all those wiggles without ever grinding it. And that's what we're doing.
The glass will be very thin, apparently all of millimeters, right?
Yeah, 3 millimeters. I know what you're going to say.
How many elements do you need? Like every few centimeters then in lateral direction? Or
Well,
you need to correct
so what we want to do is we want to measure the surface curvature, and then we want to apply the electroactive polymer so that we can use one voltage and change the local curvature with one voltage actuator.
But
So the
you need actuators in every few
No,
centimeters.
it's not. It's not like an AO mirror where we have a grid of actuators.
Okay.
It's where we have a map of the surface, and we use that map of the surface now to undo the curvature which is already there by applying with a big gantry in a 3D printer a pattern of curvature producing polymer that undoes the structure that's already there.
Okay, so you produce that once and it
Yes.
would
Yes.
under
Now, there's another problem in these mirrors, which is they're thin, and so the deformation due to gravity we also have to account for with dynamic electroactive polymers. There's another layer of glass that I didn't talk about, which has to be there to maintain the overall curvature so that we still have to have a truss of some kind. As the glass gets thinner, the truss elements would naturally come very close together, and we wouldn't gain if we couldn't use the polymer to make it stiff enough so we could separate the truss elements in distance to decrease the overall mass. So there's another piece of glass in here that manages the problem of that deformation. Okay.
Are you aware of this neural network methodology is it being applied for observations currently?
Sorry.
The neural network methodology that you were summarizing, is it being applied to observations currently? Are you aware of it?
I'm not. So we're very anxious to... we also want to use this technology for measuring surfaces with caustics. So part of our job is to take a big piece of glass and measure the surface so we can derive the curvature and apply this. And we want to do that again with a sort of neural network solution, where you have an image that you're extracting just a vector of, say, surface positions. That's a good problem for the neural networks. And so we're learning as we go that that's probably one of the fastest ways of extracting metrology in an optical system where you have a parameterized image or image information.
Just a comment about this neural network approach. We're working on using that for adaptive optics.
Yes.
And also on real-time image correction on the sun. So eventually in 1 or 2 years at the SST, you will see an image of the online corrected image so that you can click on or not if you want to observe or not.
Yeah, I was slow in learning about neural nets, and I'm completely sold. I have this feeling that we're cheating somehow because we don't really know how we're training the net, right? It's magic. But it sure does seem to work, and our experience with this problem is that it's very efficient. Now, it takes of order 1 million training images to create the function that goes from an image of speckle pattern to an output piston and tip-tilt phase. You do it only once, and you do it on a GPU. So on our big computer, we run it for a day or two to train each one of them, which is not a big deal. So I'm a big fan of convolutional neural nets. And it's a one-shot. You just take the input, you get the phases output. So it's a relatively simple neural network problem.
How easy is it to take the flat glass and make it into a parabola without putting in all the roughness that you're trying to avoid in the first place?
Yeah, so I didn't explain all of the bits here. So when we take a piece of glass, we have to make it into a parabola. And the parabola we're not going to make with the EAP. The EAP is to produce small curvature changes. We have to have a deterministic way of making a piece of glass into a parabola with a radius of curvature of several meters. That's another solution that uses this So the deformation of a thin plate is a deterministic equation that's called the Kirchhoff-Love equation. It's basically del squared of z of xy is equal to the force distribution on the surface. One solution to that equation is a parabola. And so part of what we're doing is we have a technique that uses a kiln with glass and air pressure to solve that equation in an analog way to make a parabola or to make a segment of the parabola. And that's the first step in that. But that, we're not melting the glass. So when Roger Angel makes a parabola, he melts the glass and he spins the furnace and he uses centrifugal force. But what he's left with is the de-vitrified glass. He's got to polish away of order of millimeter. So he still has to grind the glass. It's an abrasive process. We never melt the glass. We change Young's modulus by bringing the temperature up to near the melting point. And that allows the glass to slump. We pressurize so that we solve the biharmonic equation to get a parabola. And our parabola then is used in the next part of the process, which is to do curvature polishing.
Any other questions?
Totally different topic now. At the beginning of your talk, you showed these reflection curves for exoplanets where you reconstruct continents, and maybe you can bring them up, one of them again, because they were not very obvious to me.
Coming.
Yeah.
It's coming.
One more. Okay, that one. You say orbital phase, and then we have the rotation phase, the rotation period, right?
Yeah.
Why do we have within the orbital phase this very large variation of relative brightness? That is something I don't
Well, we
understand.
put the Earth in, we simulated the Earth.
Yeah, but if you look at the Earth from far away, its reflection doesn't matter where it is within its orbit.
No. There's a big difference between the northern and southern hemisphere albedo.
Yeah, but if we look at it from far away, and we look at it for a year, we always see it from the same direction. Or is it
Well, I mean, the rotation axis is always in the same direction.
yeah, the rotation
right?
is always the same. So the orbital phase of looking at the Earth from far away, the Earth should always reflect almost the same line. It depends only on the rotation phase of the Earth, but not on the orbital phase.
No, because so imagine that you're in the summertime and you're looking. So here's the star and here's the rotation. Yeah. We're illuminating the northern cap more than we are when we're over here. When we're over here, most of the illumination is on the southern cap.
Okay. I get now where it comes from. Yeah. That relative brightness is only.
No,
This is okay. This is an absolute. Yeah. Well.
Any other questions?
Okay.